Okay, good morning everyone. You guys are the die-hard heat transfer fans. Alright. So it's kind of expected because there's an exam today. Some of them will be probably writing it during the time. I will not be talking about the exam because some of them are taking it or probably will be taking it. I will not have office hours today as well, because I want to be fair to everybody. Alright, we had the review session which kind of compensated for office hours this week. Next week, I think Monday or Tuesday, I'll have the exam solutions posted so that you can take a look at it, and things will be, hopefully my grading will take about a week and a half, and I should get them back to you, okay? Alright, so to ease the mundane nature of deriving stuff, I think what I'll do today is I'll solve a problem. I'll solve a problem using fins, and before I do that, I want to very briefly recap all the equations that we have seen so far. Okay? So the fin equation is this second order ordinary differential equation, d square theta by dx square minus m square theta, where theta is T of x minus T infinity, T of x being the temperature along the length of the fin, okay, and then m square is h p k fin area of cross section. Okay, so h is the convective heat transfer coefficient, p is the perimeter, and then I have the remaining things. Kf is the thermal conductivity of the fin, and then AC is the cross sectional area. And the solution for this theta of x c1 e to the power mx c2 e to the power minus mx. C1 and C2 are obtained from boundary conditions, and we looked at a couple of cases last class. I'm just going to write down the solutions for the two cases we looked at. So case 1, infinitely long fin. So this is an infinitely long fin where L tends to infinity, capital L is the length of the fin. Okay, and the boundary conditions for this situation are the following. At x is equal to 0, which is called the base of the fin, okay, we have T is equal to T suffix b, or if I write it in terms of this theta, which is just a change of variables, theta, and x is equal to 0 is theta b, where theta b is Tb minus T infinity. And then the second boundary condition is that at the tip of the fin, and x is equal to L, this is the tip, T, and x is equal to L, where L tends to infinity. Okay, this is an infinitely long fin. And we'll see that this is kind of an unnecessarily strict requirement. Does my fin have to be infinitely long? What the hell is infinite anyways? And because of this, theta at x is equal to L, which is the difference between the two, essentially is going to end up being equal to 0. Okay, so theta at x is equal to L is C. So two boundary conditions, two constants, C1 and C2. I can solve for the constants, and so I end up getting theta of x, theta b is e to the power minus mx, no surprise, this is an exponential solution, okay. And then I can also solve for the heat loss rate, Q loss, and I had a small schematic to go with this last time. I'm just going to recap that, okay. Okay, so this is Q loss, which is the heat loss rate from the fin onto the ambient, which is the purpose of a cooling fin. And this is equal to the conductive heat transfer rate at the base of the fin. Okay, so this is equal to Q fin at x is equal to 0. This is true for all types of fins, not particularly an infinitely long fin. So this is equal to Q fin at x is equal to 0, and for an infinitely long fin, this will end up, and I'll have a set of tables online for your homework. Not this week. This week you don't have any homework. Next week also you don't have any homework. The week after that is when you have homework. Okay? Alright. So next week no homework. Just to make sure, no quizzes, no homework, for people being hopefully seeing the video online as well. So Q loss infinitely long is capital M, which is square root of theta b times square root of h t kf AC. Okay, so this is for an infinitely long fin, and then I also looked at the adiabatic tip condition. I'll briefly write that down similar to this. That's case 2. And there are 2 more cases for which we will not do the derivation, because it is just applying the boundary conditions and finding out these constants. You will do it during your homework. Okay? Alright. So case 2, adiabatic tip. And the boundary conditions are the following. At x is equal to 0, which is the same as before. So typically the base temperature is prescribed for most of the fin situations that we will be looking at. Okay, and then at x is equal to L, we have the convection boundary condition, but there is no heat transfer. The tip is adiabatic, so the conductive flux is 0, or dt by dx, which is the same as that guy is 0. So the temperature gradient is 0. If the gradient is 0, it means that the slope is 0. It's an adiabatic condition. Substituting these two, we obtain the solution. Cosine hyperbolic, okay, m times L minus x by cosine hyperbolic m times L, where little m has the same meaning as you've seen there in the first panel. And then the heat loss rate, Q loss, adiabatic tip, is just the derivative of this entire thing, and we will not be doing it, of course. We did it last time, m times tan hyperbolic m. This is the second case. I'll just write down the third case. I have derived it in my lecture notes, which I'll post after today's class. Okay, so we will not spend time doing that, and then we will go to a problem. Or would you prefer that I go to a problem now and then we come back to case 3 on Monday? Yes?
I'd say problem now, then case 3 Monday.
Okay, let's reinforce these ideas first. Alright, sounds good to me. Okay, so problem. There are 2 parts to this problem. First is obtain the condition, obtain a criterion to determine if a fin is infinitely long. So this is the first part of the problem. I'll prove this very quickly, and then we'll put some numbers and look at the next part of the problem. Alright. If I write the, so look at the infinitely long fin, okay, this panel here, all of it. If I look at the boundary condition at the tip of this fin, what's that going to be? Remember, the infinitely long fin is such that its tip is at the temperature T infinity, yes sir?
Oh, so there would be not the zero, it would be zero.
It will be zero, so this is actually a limiting case of the adiabatic fin. You see that? Does everybody see that? The temperature at the tip of the fin is T infinity. So if I write the boundary conditions at the end of an infinitely long fin, for infinitely long, essentially I'm drawing a control surface here. This is Q fin at velocities, x is equal to L, and then this is just Q convective, okay, which is going out, and if I equate the two, minus K, area of cross section, d theta by dx, and x is equal to L is h times area of cross section, theta at L, or T at x is equal to L minus T infinity. And it should be obvious that if I have an infinitely long fin, T at x is equal to L is the same as T infinity, so this entire term vanishes. And so the temperature gradient at x is equal to L is 0. X is equal to L as L tends to infinity is 0, so the infinitely long fin is a limiting case of the adiabatic tip condition. Okay? So infinitely long fin limiting case of adiabatic tip. Which means that if I compare the two, I can obtain a criterion for deciding what's an infinitely long fin. Okay, so look at this. So Q loss, infinitely long, is capital M. Q loss, adiabatic tip, is M tan h ml. So when tan h ml, tan hyperbolic m times L becomes equal to 1, I essentially get an infinitely long fin. Okay? So which means that infinitely long tan h ml is equal to 1, and in the limit of that going to 1, we get M. And so M times L is tan hyperbolic inverse of 1, which is a very weird number. It's 2.56. Okay, so if I look at tan h ml is equal to 1, if you crank up your calculators, it's e to the power 1 minus e to the power minus 1 divided by e to the power 1 plus e to the power minus 1, okay, exponential. And so we have a criterion for an infinitely long fin. If the product of m times L is greater than 2.56 or 2.6, sometimes people say this is 3, 2.56 close to 3, then you have an infinitely long fin. So for any problem, if m times L greater than or equal to 2.6 or greater than or equal to 3, if you want to be a little more conservative in your estimate, then you can treat the fin as infinitely long. The great news being, if you have an infinitely long fin, the equations are very simple. It is just an exponential decay, and I have the heat loss rate is equal to capital M. Okay. So now let's go to the problem, second part of the problem. And does this make sense to everybody? Okay. All right. So part B. In this problem, you are taking a 100 millimeter long bar. I guess let's say 200. 100 is fine. Okay. I'm taking that and I am sticking it into a wall. So I'm going to draw the schematic here. This is a 100 millimeter long bar made of some material. Thermal conductivity is given to us and so on. I'm taking this and sticking it into a wall. So here is the wall. Okay, which means that the portion that is embedded within the wall is completely insulated. Okay, so the wall is completely insulated, let's say. So I'm embedding half of this rigid bar into the wall. If I write the coordinate system here, the x-axis is the horizontal axis. So this is x is equal to minus 50 millimeters. This is x is equal to 0. X is equal to plus 50 millimeters. This is the embedded portion. I'm going to give it a subscript little e, okay? And then there is a portion that is protruding out from the wall. In the problem, they will not necessarily tell you that this is a fin. We have to figure out that this is a fin by thinking, okay, if this guy is sticking out, it's a solid body, the direction of conduction heat transfer is along the length of the fin, along the length of this protruding bar, but the direction of convection is perpendicular to it, which means that the portion that is protruding is actually a fin. Okay, so this is a protruding portion. This is a fin. This is because Q conduction is perpendicular to Q convection. Okay, so Q convection is going to take place. T infinity and H. Okay, so this is the situation that's given to us, and I'm going to call the protruding portion by the subscript F because it's a fin, the embedded portion by the subscript E because it's not a fin, so it's a part of the wall. And what's happening is that maybe by some electromagnetic setup and so on, there is some heat generated within the embedded portion. Okay, so it is Q dot greater than 0. For the protruding portion, there is no heat generation. So you're told E has Q dot of 1 megawatts per meter cube. Okay, the portion that is stuck into the wall. And the fin portion, obviously, Q dot is equal to 0. All of these are at steady state conditions. This is the assumption that we have used for all the fin problems. Okay. And I'm told the other information, thermal conductivity, K embedded is the same as K fin because this is the same body, right? The same thing that is protruding out. This is equal to some K, which is 25 watts per meter Kelvin. Okay, this is one. Then T infinity and H is given to us. 20 degrees, and H, I believe, is 100. And you're asked to assume that the fin or the bar, the entire thing is a rod of diameter 5 millimeters. Okay, so this is a long bar, which is a rod of diameter 5 millimeters. Okay. The problem tells you, okay, what is the temperature profile, what's the flux profile. So obtain temperature profile and flux profile. All right. So this is insulated. Okay, those lines that I have drawn, the vertical lines, they are not physical lines, they are not physical barriers. Those are just lines that demarcate where x is equal to 0 is and where x is plus 50 and minus 50. Okay. All right. So first thing in any fin problem, once you have identified that this is indeed a fin, is to prove that is it infinitely long or not. Okay. So let's check for infinitely long condition. Okay, so we need to prove is m times L greater than or equal to 2.6. Length is known, is the length of the fin portion, okay, not the entire bar. That's something you've got to keep in mind. And little m is a combination of a lot of creatures. We will unpack that guy now. So little m is h phi a fin a c to the power 1 by 2, or m square was hp by kf ac. And I write down these things. This is 100. Okay, this is given to us. Perimeter, it's a circular cross section, so the perimeter is the circumference. Okay, that's pi times d. Okay, this is the perimeter. Then I have the thermal conductivity of the fin material, which is 25. Area of cross section is a circle. Square, this is to the power 1 by 2. Please do not forget that factor of a half makes a huge difference. Okay, if you miss that out, and then every fin will become an infinitely long fin, your life will be easier, but you will not be happy after you get your scores. Right? And then we continue calculating this value. You can plug the numbers. M times L, which is m times the length of the fin portion, which is 50 millimeters, so 0.05. There you plug in for m from there. This gives you 2.83, which is greater than 2.6. So the fin is infinitely long. So this is how we prove it. Okay? And look at this. When we derived our fin expressions, we started off with x is equal to 0 and x is equal to L. So we cleverly also position our coordinate system. They don't give you the coordinate system to begin with. They just tell you the length of this creature is 100 millimeters. Half of that is stuck inside the wall. You set up the coordinate frame so that wherever the fin portion starts is x is equal to 0. And that simplifies the problem by a large amount, because we already derived all these expressions for the fin profile, and we just need to plug and check. Okay? Alright, so let's go for it. So between 0, x and plus L, this is a fin, infinitely long fin, which implies theta e to the power minus mx. I'm going to write this in terms of t of x, okay? Because I want to plot the temperature profile as a function of x. So theta of x is t of x minus t infinity. Theta base is t at x is equal to 0. I'm going to now give this a subscript little f because I'm talking about the fin, okay? So Tf by the base temperature of the fin, which is the temperature of the fin at x is equal to 0. This is T suffix b. We call this as T suffix b minus T infinity is e to the power minus mx, or Tf as a function of x. This is T infinity, T base, T infinity minus x. This is for this particular range of x values. In this particular equation, the only unknown quantity that I have is this base temperature T suffix b. So I do not know this guy. We know everything else. T infinity is given to us, 20 degrees Celsius. M, we just calculated that fellow. Okay. So one of our aims is to calculate T suffix b using the information given. But hold on to your thoughts. Take the differentiation of that. Write the heat flux as well. So Q double prime fin is minus K fin d theta by dx, which is the same as dt by dx. If I do the differentiation of this expression, Q double prime fin is going to end up being the following. So this is going to be Kf times little m dB T infinity minus x. And I want to see if there are any questions so far. All I did was take the expression for T of f and then differentiate it. Okay, so nothing fancy. Alright, so that's the situation. And we have all of these values here. I'm going to take off this particular panel of the board if everybody is done with it. Okay. So we're done with the fin portion. I have one unknown that is to be discovered there. Hopefully boundary conditions will give us something. But then I have this portion that is embedded within the wall. So I essentially use the 1D heat diffusion equation. Starting from x is equal to minus L to x is equal to 0. Because this is nothing but a plane wall. Right? So if I use the 1D HDE, so for the embedded portion, you can use the heat diffusion equation for any body where there is conduction that is taking place. It is not particularly restricted to a plane wall or a fin. And we obtained the fin equation by using the conductive heat transfer equation, but of course there was convection taking place on the surface of the fin. Okay, so embedded system here, K times d square Te dx square plus q dot is equal to 0. This is all old stuff, nothing to think about. Yes sir, question.
Why don't we use the HDE for a cylindrical body? Because isn't it a rod?
Right, but then you can think of it as that way. We could do it that way, but let's see. Your direction of heat transfer is along the length here.
So we
It's
don't
not
care
along
about,
the radial direction.
So if we care about radial, we use that one.
Right. Because of the fact, you see, cleverly they said that the top and the bottom are also insulated,
Okay.
besides the side.
Okay.
So that's why you can't use the cylindrical. That's a good question. Let me clarify that here. So cannot use, so even though this is, the rod is a cylinder, the conduction Q conduction is along the length of the rod and not radial. And so we use the plane wall heat diffusion equation. Yes.
If the top and bottom of the rod were not insulated, we would have to use a combination of the two, and it would make everything complicated.
You would have to, so then the direction of heat transfer is purely radial, so which means that the heat going in here is going to be kind of tricky, right? So the heat has to be transferring in the axial direction, which means that you will have to use a two-dimensional heat diffusion equation. So where there is axial direction as well as there is radial heat transfer. Or in some sense you can say, okay, hey, if that is the case, and I'm knowing only the 1D heat diffusion equation, then I'm going to have an insulated condition here, I'm going to have an insulated condition here, and this fin is basically just a useless protuberance. It does not do much to me. Okay? But that's our limitation. That's not the limitation of the fin, per se. Alright, beautiful. So let's keep going here. TE, integrated twice and all those things. TE is minus Q dot x squared by 2k C1x plus C2 for, be careful, the limits for this is minus L, x and 0. Okay. And I'm going to take this portion off so that I keep working at all of these details that we have. Alright, now we start using the boundary conditions. So embedded portion. First boundary condition, please be careful here, do not say that it is insulated at x is equal to 0, it's at x is equal to minus L. Okay, so at x is equal to minus L, dTE by dx is equal to 0. So that's the first thing. Let's substitute this, okay? So dTE by dx at x is equal to minus L, so that's minus Q dot times minus L by k plus C1 is equal to 0, or I can obtain C1 this way. I know the length, I know Q dot, I know thermal conductivity. So C1 is minus Q dot L by k. What's the second boundary condition? So how many unknowns do I have? TB, base temperature of the fin, C1, C2. There are three unknowns in this particular problem, right? As you can see, TB is not known. We have used one boundary condition to calculate C1. I need two boundary conditions. The boundary condition at the end of the fin has already been applied. It's an infinitely long fin with an adiabatic tip and so on. So the only boundary condition that is left is at the interface between the embedded wall and the fin. And it should be fairly straightforward to realize that this is going to have a continuity in temperature, and it will have a continuity in the flux. Okay? And so not necessarily a continuity in the slopes, because the temperature profiles are completely different. For a fin it's an exponential condition, this is a quadratic, so there is going to be a slope discontinuity for the temperature even though they are made of the same material. In one of your homeworks you had a wall with different materials and you saw that there was a slope discontinuity. In this case, even though there is the same material, their behavior is of two different creatures, so they are not going to gel well with each other. Okay? Second boundary condition is that at x is equal to 0, I'm going to have continuity of temperature, so TE at x is equal to 0 is T fin at x is equal to 0. Alright, and if I do the substitution, TE at x is equal to 0 is C2. T fin at x is equal to 0 is the base temperature, so if you want you can substitute here. It's going to be T infinity plus TB minus T infinity, which is TB. So that's the second thing. That's calculated. And then the last one. I'm going to keep these. There is flux continuity at x is equal to 0. You can draw a control surface and show that if you would like. Whatever is coming in here has to go out, and I'm looking only at the flux balance. Okay? Same cross-sectional area, so, or if you like, Q double prime fin times area of cross section is Q double prime E at x is equal to 0. Alright. So let's do this very quickly. I already have an expression for Q double prime fin. Cross sectional area is same on both sides, so I cancel it off. This is energy balance, surface energy balance. Substitute for x is equal to 0, so this is Kf times m. Kf is the same as K, so I can just write it as K. K times m times Tb minus T infinity. This is equal to Q double prime of the embedded portion at x is equal to 0 is just going to be C1. Okay, so this is equal to C1, where C1 is minus Q dot L by K. But I've got to be careful. It's minus K times C1, I'm sorry, it's a flux, so that's K times dt by dx. So dt E by dx is C1, and minus K, K and K cancel off. So that Tb is T infinity plus Q dot L by M. Okay, if I just substitute for C1. C1 is right there. All the numbers are known to me. T infinity is 20. Q dot is 1 megawatt per meter cube. Length is 50 millimeters. Little m we calculated some time back. So just plug in those numbers, and you'll see it in my work when I post it on Carbon. Tb is approximately 55 degrees Celsius. Okay, so this is the base temperature. And obviously Tb is the same as C2, so you can link the two. Alright, so in summary, this is what we have. The problem is done, but I just have to plot the flux and the temperature profiles. So I have Te is minus Q dot x squared by 2k, C1 which was minus Q dot L by k multiplied by the factor x, plus C2 which was Tb. Okay. Then I have Tf as well. This is for and Q double prime E is minus k times Q dot x by k q dot L by K. This is for the first range of x values from minus L to 0. So I'm going to write this here, minus L, 0. In the next set, the f is t infinity, tb minus t infinity minus m is all those things that we calculated. So kf times m and this is for a different range of x values from 0 to L. And as we go further in heat transfer, you'll see that things will start getting a little more out of hand. This is just something to note. But you got to look at the underlying theme of all of these things. There is just one thread that connects the whole thing together. That is the first law. If you know how to apply the first law, and if you know how to do surface energy balance and control volume analysis, this is essentially just taking different pieces of a trick, combining them together, and then coming up with the answer. It just looks a little nasty because of all these different types of equations, but in reality it is not that bad at all. It is fairly straightforward. Heat enters, heat goes out. What's more complicated than that? Okay? Alright, temperature profile. And then flux. This is L prime, x is equal to minus L, 0, this is t, minus L, both of them are functions of time, functions of distance. Okay? Alright, I start with the temperature profile. If you want, you can calculate the temperature at the end x is equal to minus L. You will end up having a much higher value because there is heat generation taking place. So I start off as adiabatic, so 0 slope. And then we know that the direction of heat transfer is going to go from x is equal to minus L all the way to x is equal to L. And so the profile has to follow the following curvature. This signifies that the direction of heat transfer is along the x-axis. Positive x direction. This is a quadratic profile. There's going to be a slope discontinuity, but you can figure those things out by substituting. And then the remaining portion is going to be an exponential decay because that's the fin portion. So this is the embedded portion. This is the fin portion. This is exponential. There is a slope discontinuity, please notice. The slope here versus the slope there. So this is the temperature profile. And then we have the heat flux profile. At x is equal to minus L, the heat flux is 0 because the wall is insulated. And as you can see from the expression here, the heat flux is linear with respect to x, so it is increasing. And I know that the heat flux is positive because the heat direction is positive along the positive x-axis. So my heat flux starts from 0, goes all the way up, reaches a point where there is continuity between the embedded and the fin portion. This is linear. And obviously I know that this is an infinitely long fin, the tip being adiabatic, So I'm gonna have an exponential decay where the heat transfer rate eventually falls down to zero, right? So this is going to be an exponential